Okay, we have a skier going down the hill, and we're asked to use conservation of energy to find the final speed, but we have some friction involved. So this is conservation of energy with a non-conservative work term thrown into it. So what we're ultimately going to use is we're going to say like this. My initial energy was gravitational potential energy. The skier started from rest. And my final energy that's going to come out of this is kinetic. My skier now has this motional energy. At the same time, work is being done by a non-conservative force, and it's friction in this case. And certainly the work done by friction in this case is negative because the force of friction points opposite to the sliding direction, giving me a negative work. So I've got to figure out the force of friction, and to do that I need to do some force analysis. All right, so now I'm doing some force analysis because I'm trying to figure out what's the force of friction on the skier. That will allow me to compute the work done by friction. So mg pointing down as usual, and a tilted coordinate system as usual. And this angle of elevation is 8 degrees. And it's the same as this angle right here. And I end up with a perpendicular component of that gravitational force. It's going to be a mg cosine theta. And there's no acceleration perpendicular to the incline. So my normal force has to be equal to that perpendicular force, mg cosine theta. And then finally, there's friction opposing the direction of slipping. So that's a Fk given by mu k times the normal force. And there's not really room to put any numbers in there, so I'll just leave that as it is. For completeness, I could look at the force of gravity pointing down the slope, but we're going to account for the work done by gravity using energy instead of directly calculating the work. So there's that. All right, so in my initial state, I have to write down like all the different types of energy that I have going on. And it's just gravitational potential because there is no kinetic energy yet. I suppose I should put in that y is equal to 0 at the finish line here. And then here I'll just call this y initial. And I'll go ahead and mark in here that this is 20 meters long. All right, so let's get the initial energy written down. And I'll show you maybe a little different style of doing it. All right, this is being extra thorough. I'm not putting in the zeros right at the beginning, but I know the initial velocity is 0. And then I have the work done by friction, and that's going to be a negative number because it points in the opposite direction of the displacement, Fk times the total distance that it acts through, which is 20 meters. And then my final energy, I end up at a y-coordinate of 0. So mg y final is going to be 0. And I have some kinetic energy. And that's it. So it's a little bit weird dealing with minus signs sometimes when it comes to energy, but this is the correct way to write it down. Energy conservation when a non-conservative force is acting. E initial plus the work done by the non-conservative force. And that work done turned out to be a negative number. So there's friction deleting some energy from the initial amount. I can do problems where I throw in a non-conservative force that's pumping energy into the system. Like suddenly you fire a rocket and it pushes something faster than it ordinarily would go. And you just put it in just like this, but you would put it in a positive number instead. Okay, so I have, putting in a little more detail, mg y initial minus mu k times the normal force, which is mg cosine theta, times the sliding distance, equals 1/2 mv final squared. And I'm going to have to do a little bit of work to get the initial height. So I have the slide distance and I have the angle of incline, but I need to find the initial height. So that's kind of a side calculation. And I could say, like this sine, well, we do this so often with vector components that I'm just going to say it. I would say that the height, or the length of this side here, is going to be the hypotenuse times the sine of the angle. And I'll get a decimal on that. And I get that it's 2.78 meters. And then I think I have everything I need to just wrap things up. Turns out the mass of the skier doesn't influence how fast they're going at the bottom. And I have 9.8, initial height of 2.78, coefficient of friction of 0.1, 9.8 again, cosine of 8 degrees, slide distance of 20 equals 1/2 v final squared. So I'll smash all those together. Okay, so I get a 7.83 over here. Let's keep an extra decimal point, equals 1/2 v final squared. So I'll multiply by 2 and square root it. And I get 3.96 meters per second. So again, this is a problem we could have done with our old techniques. We could have used Newton's second law to find the acceleration of the skier and use the acceleration and the distance, use the kinematics formulas there to get the final velocity. This gives us an alternative way to do it that in a lot of cases is much simpler and sometimes is the only way to do a problem.